Okay, in 4.6, we're going to look at two methods of numerical integration. So approximations. They're just trying to get better approximations than the rectangles got us, because if we have functions that say are difficult to take the integral of, or we don't have the tools to take the integral of, we could still get a pretty good approximation. And so the first thing they tried, it probably is kind of logical if you think about it, is instead of making rectangles, they tried to use trapezoids, because the trapezoids can be a different height at the top and bottom, and so you can more closely follow the function, so you don't have that huge over-under estimate thing next to it. And so picture, if I'm going to do that, how do I come up with the area of a trapezoid? Well, a trapezoid has two different heights, and so I want the width, which we'll stick with our notation and call it delta x. So the width delta x times, and this comes from plugging in a function. So let's say if this is the starting point x0, let's say this one is f of x1, and this one's f of x2. I will say in this other, if we were doing the other one, it'd be f of x0. You take the two heights and you average them. And so then you have a width times an average height, because the height of the thing is changing. And so then notice if I take a bunch of these, and I more or less connect them together. That one is a little wider. Oops. If I use 1, 2, 3, 4 subintervals, notice I'm using f of x0, f of x1, 2, 3, and 4. So if I was trying to do a sum, one thing to notice, and we won't go through the whole proof, but one thing to notice is that this height gets used once, but this one gets used on this trapezoid and on this trapezoid, because it's on the right of the one and on the left of the other one. And so if you go to add these all up, this delta x, and notice if we're doing subintervals, that is our b minus a, how far we're trying to take the integral divided by the number of trapezoids we break it up into. And then this 1/2 can get pulled out front. And so really what we're trying to do is take the sum of all these different heights. And so when you look at trapezoid rule, you can kind of see those pieces in it. So it's saying one good approximation for this, or I use the squiggly equal sign, it's approximately equal to, not the same as. So here's our half and our n. And then we take the first point plus the second height ends up in there twice because it's on the right of one trapezoid and on the left of another one. And so all of the middle ones end up in there twice until the second to last one, and then the last one, x sub n, if we're doing n subintervals, only ends up in there once. Okay, so then we can try one of these on an actual function. So let's go with one we know how to do exactly, so just so we can do it exactly after and see how close we are. So if I want the integral from 0 to pi of sine of x dx. So what's my b and what's my a? Well, I'm going from 0 to pi, so b minus a is pi. And they'll tell you in it how many subintervals they want you to use. So let's do a relatively low amount so it doesn't get really tedious. Let's do n equals 4. And remember from rectangles, 4 rectangles would probably be a pretty bad approximation. We'll see if it turns out any better when we do this. So if n is 4, you end up with 2 times 4, 8 under here. So then what are the points I'm putting in? Well, think if I'm going from 0 to pi and I'm breaking it up into 4 subintervals, the first one's at 0, the next one's pi over 4, and then 2 pi over 4, which is pi over 2, and 3 pi over 4, and then all the way to pi. So I want to know what's sine, because that's our function here, right, of 0, plus 2 sine of pi over 4, plus 2 sine of 2 pi over 4, so pi over 2. My third one, 3 pi over 4. And then just like we talked about This one and this one are endpoints, are only in there once, but all the middle ones are in there twice. Okay, so then we just have to evaluate these. So we'll leave the pi over 8 on the outside, and then sine of 0 is 0. This is 2 times square root of 2 over 2, so the over 2 cancels with this one, so it's just square root of 2. And then this one gives you 1, sine of pi over 2, right? Sine of 90, so you get 1, and so 1 times 2. This one's also pi over 2 pi, or square root of 2 over 2, so the over 2 part cancels. And sine at 180 is 0. And so if I add these all up, it's approximately equal to, and this is one of the few times where it's totally okay to put an approximate answer, because these are by nature approximations. And so I like to see a decimal because I want to know how close is that to the real answer. So I got 1.896 with 4 trapezoids. Okay, then because this is one that we definitely can do using our normal methods, let's do this one by hand and see how close we were. So 0 to pi, sine of x dx. The antiderivative of sine is cosine, but then think you need the negative, because when you take derivative of this, you want the negatives to cancel. And then you're doing cosine between 0 and pi. So negative cosine of pi minus negative cosine of 0. So this gives me cosine at 180 is negative 1, so negative 1 gives me 1, and then minus a negative here cancels, and then cosine at 0, so the x value at 0 is 1. So it looks like the exact answer for this integral is 2, and we got 1.896, so like 0.11 or less than 0.11 off, only using 4 trapezoids. So even if we went up to just as few as like 6 or 8 or 10, we could probably get a really accurate estimate.